Physics is inherently continuous. Water flows, orbits drift, and waves propagate in smooth, unbroken curves. But when we try to model that physical reality on a computer, we hit a hard limit. Hardware is strictly discrete. Everything must eventually resolve by crashing into a rigid, finite grid of ones and zeros. To get around this limitation, modern mathematicians use enormous software libraries, like MATLAB in the Lean programming language, to simulate continuous infinity. But simulating infinity introduces a critical vulnerability. The moment you invoke an uncomputable limit, you stop calculating and start asserting. You are relying on philosophical axioms that the machine cannot physically execute. By relying on a simulated continuum, the proof loses its mechanical certainty. There remains a blind spot at the foundation of the mathematical model. There is an alternative approach. In the codebase we are examining today, the author strips away all those external math libraries. They force the compiler to rely exclusively on its bare minimum init logic. This imposes an absolute constraint on the mathematics. The system is no longer allowed to assume a continuum exists. It can only verify what it can explicitly count, step by step, and terminate using a strict compiler command known as native decide. This rigorous restriction is what the author calls the bounded shadow. Instead of trying to compute an infinite curve, the system proves continuous mathematical theorems by calculating their exact boundaries on a dense, rational grid. It maps the finite boundary that the infinite concept casts. Calculating a rigid, finite shadow provides a structural proof where every single node is mathematically verified in memory. Look at this continuous circular contour, plotted here on a complex plane. This is the standard geometric shape used for integration in classical complex analysis. A machine cannot natively compute every infinite point along this smooth curve. So the bounded shadow methodology snaps the circle into a 16-point square grid, hard-coding a discrete boundary. The exact mathematical locations of these vertices are defined using rational complex, or QC, coordinates. These are precise fractions, avoiding the rounding errors inherent in standard floating point decimals. To perform discrete integration, the computer evaluates the path segment by segment. It hops from vertex zk to the next, tracing the entire sequence around the 16 points to close the loop. Squaring the circle into a rational path converts an unsolvable infinite integral into a terminating arithmetic loop that the hardware can process. We can apply this discrete contour to the classical argument principle. Normally, this theorem calculates how many zeros a polynomial contains inside a defined area. Let's test the polynomial z squared minus 1. Inside our 16-point unit contour, this function has two distinct roots, mapped here at 1 and -1. The discrete system verifies these roots by calculating the topological winding number. It tracks the mathematical phase as it races across the contour, iterating exactly twice as it registers the influence of the two roots. When the sum of the imaginary axis crossings evaluates correctly against the predicted count, a simple Boolean condition triggers a success state in the compiler. Identifying polynomial roots by physically counting their boundaries within a discrete space bypasses the need for abstract algebra. The topology is verified by raw arithmetic. Another pillar of complex analysis is the Cauchy integral formula. Computing this requires evaluating a singularity kernel, specifically dividing by 0 at a target point z0, an operation that normally crashes a program. To prevent this, the code employs escape hatch logic. If the distance to the target point evaluates to 0, the logic catches the singularity and returns an explicit 0, keeping the function safely bounded. The system then applies a hard-coded parameter called Cauchy-tal, set to exactly 1/2. This forms a rigid, unmoving bounding box around our target point. The system accepts the theorem's validity only if all the discrete approximations land entirely inside this strict fractional box. This check ensures the result is contained. If the calculation falls within the tolerance box, the proof holds, defining truth as a strictly verified bound. We see the same strict logic applied to the Schwartz lemma. The continuous constraint states that a specific function mapped onto a unit disk cannot produce an output value larger than its input. Exhaustively checking an infinite disk is impossible for a computer. Instead, the framework constructs a unit disk grid, populating the space with exactly 45 dense rational coordinate points. This is the discrete shadow. If we apply the function f of z equals z squared across this grid, the 45 points calculate their values. Visualizing the outputs confirms the distance from the origin consistently shrinks or matches the input distance. Iterating this mathematical check over these 45 distinct rational nodes satisfies the compiler's need for exhaustive proof. If a spatial constraint holds true across an optimized rational grid, the underlying topological reality is definitively bounded. The source code contains a definition called Schwartz unbounded, which explicitly identifies the limit of this discrete framework. The system hits a hard boundary. It cannot prove the universal for all functions statement. Compiling an infinite number of continuous variations is mathematically impossible. Formal rigor depends on these boundaries. Defining the point where computation stops establishes the specific reach of the system's logic. We can scale this integer logic out of abstract mathematics to see if it maps against the physical universe. A module called Bythoscale rejects standard floating point physics measurements. Instead, it substitutes a static, microscopic integer base unit to construct a scale hierarchy. It sets the floor of reality, the Planck length, at 10 to the negative 39th power meters. Using a decadal ladder, the code maps logarithmic integer jumps to climb from the scale of a tiny proton all the way up to the observable universe horizon. Reality is mapped here as a finite sequence of logarithmic steps. The logic depends on these boundaries, providing a model that exists strictly within the limits of computable information.